Hello and welcome once more to our presentation entitled Solving Initial Value Problems, a full menu solved example. This is part 2 of our previous presentation. Our outcomes are still the same and we quickly proceed to the example. Remember, we started with the example which was given as follows, and please note the important steps in solving these problems. First step, you are given the equation with initial values. So you've got to transform the time domain differential equation to an equation in a frequency domain, which you actually solve using well-known algebraic skills. In this case, this consists in simply making the unknown in the frequency domain, which is x of s, which has been transformed from the time domain as x at t, landing the frequency domain as x, capital letter X of s. So our solving the equation in the frequency domain means giving x of s as a subject formula, which we had already done here, and we noted that we got this kind of a complex rational expression in terms of x, which we had to simplify in order to get expressions which are similar to those Laplace transforms which appear on the table. So that took us to factorizing this cubic expression and then decomposing the complex rational expression into partial fractions with unknown constants a, b, c, and d. So our task now is to proceed with this and see what further manipulations can we do in order to get expressions which appear on the Laplace transform table. We now consider our x of s, which we've got two ways, expressed in two ways, as a single fraction and as partial fractions here. Our target is to find these constants which are unknown. So we multiply both sides by the common denominator, which is this s in brackets s plus 2 multiplied by s squared plus 4x plus 6. When we multiply both sides by this common denominator, we get the following on the left hand side equals to, what is important here, you must know that this expression is an equality for any value of s. So I'm going to choose the values of s conveniently in such a way that I can be able to determine the values of the unknowns a, b, c, and d. So first of all, let's set s equals to minus 2. If you set s equal to minus 2, you can see that there we're going to get a 0 and there a 0, meaning these two terms are going to vanish, and then we're going to be left with this term and the left hand side, which in this case is going to give us equals to on the right hand side, and then here we get minus 4b equals to minus 7 there. Therefore, b is equals to 7 over 4. Proceeding, we can now set, let's say this is our initial option there. Then next one, and after working with s equal to minus 2, let's now consider s equals to 0. You know that if s equals to 0, the left hand side is simply equals to 1, and on the right hand side we'll have these two expressions vanishing. Then what we have here, we are left with 2 times 6, which will give us 12a, and then we can conclude here that a is equals to 1 over 12. So now we've got a and b. We need to proceed to get to c and d. Then on the left hand side here, if we get x equal to minus 1, we are going to get equals to minus 7. On the right hand side, if we take minus 1, note that now here we've got the values of a and b. Then we have to substitute here a by 1 over 12. I arrived at that c minus d is equals to minus 5 over 2. And then in the fourth case, we consider s equals to 1. Doing exactly the same kind of work, I am now substituting by 1 in the same equation, doing similar calculations. This gave 3c plus 3d equals to 22 over 12. Solving the two simultaneous equation delivered c equals to minus 11 over 6 and d equals to 2 over 3. So now, once we've got this, we simply need to go back to our expression and substitute, and then simplify further to see if we get this also looking like Laplace transforms which appear on the table. Already we can see that this, if we've got b and c, already can figure out what functions are represented by this part. Now rewriting this, having the values of a, b, and c, we have, and the last term we're multiplying by 2 over 3. Now you'll notice that in our Laplace transform tables, we don't have an expression which is in terms of a quadratic power of 2 of s with 3 terms. So, but let's look carefully at what we have here. In order to proceed, we need to consider completing a square in this denominator. Then we'll get some kind of an idea which Laplace transform we're talking about here, because such a Laplace transform with this kind of denominator we don't have on the Laplace transform table. So we now look at, and the completing a square here, break this 6 into 4 in 2, and you note that this gives us a perfect square, which is s plus 2 all squared plus 2. What we have, for example, in the case we've got 1 over this denominator, we can now write it as s plus 2 all squared plus 2. But a Laplace transform which has got this kind of shape, which we know is omega over s squared plus omega squared, which we know that its inverse transform is sine omega t. But what we have here, if we didn't have this 2, we would have x squared plus 2. 2 then is equal to omega squared, where we can conclude that omega is equal to square root of 2. So then, which means now we can rewrite this as 1 over s plus 2 plus square root of 2 squared. Now our problem now is the numerator of got 1 instead of omega, but we know that 1 is equal to square root of 2 over square root of 2. So which means here we've got the numerator being square root of 2 over square root of 2 all over s plus 2 all squared plus square root of 2 squared. And we know if we've got a over b all over c, this will be equal to a over bc. So you can take your b here to be square root of 2, then we remain with square root of 2 all over square root of 2 in brackets s plus 2 squared plus square root of 2 squared. Now if we look at this now, we've got omega squared and the s plus 2 squared. So which means here, if this was an x of s, this will be an x of s plus 2. So which means this calls for an exponential shift theorem. Then again, looking at the expression where with s with the same denominator, which you can also write as s plus 2 squared plus square root of 2 all squared. The problem we've got here now is not with omega but with s. This actually looks more or less like the transform of cosine function, which actually looks as s over s squared plus omega squared. This would transform to cosine omega t. But now here the problem in this transform, here s is s plus 2 and there is simply s, but to be of this form we must see that there is sort of kind of a harmony in terms of what these two terms are written in terms of here. So this is s and there is s, so here is s plus 2, so they must have s plus 2 also. So how do you create that? We'll simply write s plus 2 minus 2 all over s plus 2 squared plus square root of 2 squared. You can see that what I've done here, I've just simply added 0 conveniently, and this is actually equals to s. But this takes us to splitting this to s plus 2 all over s plus 2 squared plus square root of 2, and this side we've got minus 2 all over s plus 2 squared plus the square root of 2 squared. So now if you look at this expression, it takes us back to this kind of problem which we had here, where we had omega here but no omega in the numerator. But note that 2 is simply equals to square root of 2 multiplied by square root of 2. Then, so what you can do here, we can actually write 2 in this way and take 1 square root of 2 as a factor outside the brackets. So this will end up with s plus 2 over s plus 2 squared plus square root of 2 squared. And then this side, taking 2 in this way, we can write minus square root of 2 here, and then in brackets. Then that way, again, we can now see that these two expressions again they need the exponential shift theorem. So which means for the last term we're going to have 3 terms, this term and that and the one we have got here. So now rewriting the expression we have arrived at here, this giving us this two expression and that giving us that, plus the first two terms here. At this point, we now see that we are ready to simply write the time domain signal using the exponential shift theorem. But just before we proceed, I would like to call attention to the strategies used here. Note that we're to complete a square. That is something you must also be very, very fluent in. And after that, we modify this expression in such a way that it sort of fits or matches the exponential shift theorem. And then getting to this point, you see that you get your numerator not really being omega. So this kind of transformation is something which you must be familiar with, and without practice it's very, very difficult for this thing to occur in a test or whatever. You have got to come across this thing in your practice before you can do it for any type of evaluation. Similarly, coming to this manipulation here, is very important that you understand what we've done here. Like for example, to change this S to look like an S which matches the exponential shift theorem, were to add a plus and minus 2. The reason why I added a 2, it was actually motivated by this S plus 2. So I saw that if I add S, subtract 2 there, I would achieve that, then end up with these expressions. So these things need very, very serious practice if you are to be able to do this exercise successfully. So coming back to our time domain signal here, we'll now simply write this, therefore x of t, and as you can see here, if you get to the table, this is actually the Laplace transform of the unit step function. So we're going to have here 1 over 12 multiplied by ut, but I'm going to just write ut at once outside the brackets. Then here we note that we've got an exponential shift theorem here, because this is 1 over s. Without an s, it's just a constant. But with this, it's now 7 multiplied by e to the power 2t for the exponential shift all over 4. And we've got the exponential shift again, which is e to the minus 2t. Then we write here 11 e to the power minus 2t all over 6. And you can see that this is a cosine of omega, which is square root of 2 multiplied by t. And then here, we multiply this 11 by that. We get minus 11 square root of 2 all over 6 multiplied by the exponential multiplied by sine omega, which is square root of 2 and t. Then here we end up here with 2 over 3 square root of t e to the power minus 2t sine square root of 2t. All that multiplied by the unit step function, to emphasize that we were talking about causal signals here. So this will be the solution of the differential equation given. Now, if you look at this expression, we can talk about some of the things we've seen before when we're discussing dynamic systems. So if you look at t, you notice that if we look at t to the limit as t is going to infinity, all these terms here are multiplied by a decaying exponential function. So which means all of them, they are going to individually tend to 0. So the limit of x of t as t is tending to infinity will be 1 over 12 ut, which is essentially a constant function from 0 to infinity. So it will be 1 over 12 there, and being a constant function. What does it mean for a dynamic system? It means simply that as time is passing by going to infinity, the value of this expression actually is a constant. In other words, you can also express that as that this system, its value cycles at 1 over 12. So after a long time, this signal will look like a constant function x of t equals to 12, starting to manifest where at t equal to 0 as a causal signal. So that also we can refer to as the final value of the function. In this case, we're given the initial value of the function, and now we're talking about the final value of the function. So in our next presentation, actually, we are also going to talk further about initial values and the final values of the function, how to determine that. Otherwise, at this point, we have seen from our previous example to this example, we've seen all the steps which are necessary to solve an initial value problem using the Laplace transform. So summarizing, I hope we saw what we did there we're given a differential equation. So the first thing is to apply Laplace transform to take it to the frequency domain, where we get an algebraic equation, which we solve by simply making x of s subject the formula. Once we've done that, then we're getting involved in these issues of simplifying or decomposing rational fractions into partial fractions, which, as you have seen, it needs a lot of things to remember, from factorization, completing a square, division of polynomials, and so on. Then after this, then we apply the inverse Laplace transform to get back to the time domain signal, which will be the solution to this given initial value problem. Basically, that describes the whole process. So now, for a practice for this work, I leave you with the following 3 examples as your initial practice. I hope you are going to manage to face the challenges involved here. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Wasfani Msip.